This object was selected because of its size, star formation, and prioritized because of its intriguing visual morphology in the Hubble imaging. Here you can see that there are several bright clumps that appear to be connected by wispy bridges of gas, and there's no clear center. And as Susan said earlier, we selected this because we thought it would be an amazing merger to study the gas kinematics of and other spatially resolved properties. But shortly after submitting our observation plan, images from JADES came out, and our jaws just dropped. This is a beautiful image, and you can see that the clumps are still there. Some have been broken down to even smaller clumps, but you can see that there's evidence for more evolved structures such as spiral arms, a central bulge, and perhaps even a bar. And here I show the RGB images broken up into the individual band passes. And I show this to emphasize that in the near UV, rest frame near UV, so these two panels, this galaxy is very clumpy. The hallmark of a merger is that there's gas in the center. And as we move to the rest frame near IR, which begins to reveal the backbone of the galaxy, we see these more evolved structures such as the spiral arm and then a bar-like feature, and it's just beautiful. And before we get to the kinematics, I want to show this image, which is summing up all the available bands from NIRCam and applying an unsharp mask to pull out the really faint stuff that's in the image. And it's better on my computer screen, but you can see that these spiral arms begin to, go further out in the galaxy. And if they are spiral arms, it's a pretty tightly wound spiral. And I won't take too long on this because Susan spent a good amount of time on it, but we obtain IFU-like data for this galaxy thanks to the slitlet stepping technique. We're going to be here all week. Please talk to us if that interests you. And now I'm going to jump right into the H-alpha kinematics. So from left to right, you have the JWST postage that I've shown on the previous slides. And in the middle, you have the observed H-alpha velocity, where pixels colored red are moving away from you into the screen, and then the blue pixels are moving towards you. These are observed quantities, so they have not been corrected for the effects of inclination, so these values are higher intrinsically. And then lastly, you have the H-alpha velocity dispersion. These maps show exquisite detail. The velocity has a strong sense of rotation and an S-shaped zero velocity line, which is kind of a hallmark of a bar. Or it could also be from a merger, but it's hard to tell from the IFU data alone. And then finally, in the H-alpha velocity dispersion, it peaks in the center, which is what we may expect for a disk at intermediate redshifts, but the elevated velocity dispersion is also extended in the disk in these inter-arm regions. And I'm going to come back to this a little bit on my final slide. So what might be going on in this galaxy? It has a beautiful blend of disk and merger-like properties, and given its elevated gas fraction, about 0.7, we believe that this could have formed from a gas-rich merger, and this nicely supports results from simulations, and I'm highlighting that people here really spearheaded that, including Brant Robinson, James Bullock, and Phil Hopkins. And just to conclude, this object's really interesting, and I don't think the most interesting question that we can answer of this galaxy is it a disk or merger? I think we are starting to, unveil some really interesting things that we can pull out. Here, I put the contours to the near UV flux, and you can see that these bright UV clumps are in regions of low velocity dispersion. Again, maybe we're observing regions of low TUMRE-Q, but also the regions of high velocity dispersion just completely meander around these contours. And, I might not have dug further enough, but, I haven't seen this produced in simulations, and also this is different from what we see from ground-based IFU surveys of Redshift 2 galaxies, as well as in MANGA, these high velocity dispersion values in the inner arm region. And to conclude, I just want to ask the simulators in the room, do you see this? What causes it if you do? If you don't, I would love to talk with you and maybe, hear what you think what might be happening, because I'm getting really interested in velocity dispersion, and our data are starting to, show interesting things. And I'm going to just end it here, and I'll be happy to take some questions if you have any.
Thank you, Celia.
Oh yeah, of course. Seminar. There we go.
All right, any simulators want to take this on?
Model my galaxy.
Or other questions for Celia?
Hi, thank you for the talk. I have a quick question about the Bear Cloud Galaxy here. I know it was asked in the previous talk whether or not there was ALMA or MIRI coverage of both of these galaxies. Yes. Do you have any X-ray? Also, I'm wondering what the chances are of there. You have a dusted galaxy here, kind of cosmic noon. If there is maybe a buried AGN there.
Yeah, this is a good question. So. There is no archival X-ray data on this object. It's within the SMILES footprint, which is MIRI imaging, and then there is a decent detection in ALMA. It's not within the I think it's a 3 sigma detection in ALMA, mainly going for dust. But I've looked into kind of some line ratios. We don't have O3 or H beta, so we can't do a BPT diagram. There could be a low-powered AGN in the center. I won't rule that out, but there's no smoking gun evidence of a very powerful AGN residing in the center of this object.
Okay, one last question, and then we'll transition to the discussion.
You mentioned you see spiral arms pretty wound up, but then you also advocate a merger scenario. Now, if there were a major merger, the disk probably would be wiped out.
Okay.
So it's hard to imagine that could stay.
I'll have to disagree with that. At this redshift, there's so much gas that you actually keep the disks when you merge. All right, let's thank Celia again.
Thank you.
And hand it over to Susan and Kate.